Welcome to Chemistry Tales. This is Tale 1, Track 1, Acid-Base Equilibria.
So, the next important thing we need to recognize, what kind of acid or base or type of solution are we dealing with, because that tends to dictate how we approach solving questions like hydroxide ion concentration, pH, etc. Okay, so let's start with the different kinds of solutions, types of solutions we might be asked to deal with, starting with strong acids. Okay, by definition, a strong bronzed acid is going to fully dissociate, break up into ions. All right. Best way to recognize a strong acid, there's 6 of them. Just memorize them. It's easy. Hydrochloric, hydrobromic, hydroiodic, all halogen-based molecular substances, nitric, sulfuric, and perchloric. 6 strong acids. These substances, when placed in aqueous solution, will fully break up into the corresponding hydrogen ion and anion. For example, nitric, when placed in aqueous solution, is going to break up into a hydrogen ion. Okay? Structurally, if you take away 1 hydrogen, you're left with NO3, and we must have charge balance. If we take away a positive charge, that means in that bond we left the electron, so there's 1 extra electron, and the nitrate ion has the negative charge. That's polyatomic, we should recognize. All right, so this is the simplified way of representing this. Remember, we are truly in aqueous solution. Water molecules are around. So the reality is the water molecule is actually the carrier of the hydrogen ion. So if you want to write it this way, you can. It's more technically correct. So we're forming the hydronium ion, hydrogen ion, given to the water molecule, leaves the nitrate ion and the hydronium ion. Okay, so this is the simplified version. This is the more technically correct version, both acceptable. So if I start with a solution in which the concentration of the nitric acid is 0.02 molar, what is the hydronium ion concentration in that solution? What is the pH?
And he's being a good help, isn't she?
All right, so first of all, we recognize that this is a strong acid. Strong acids fully dissociate in aqueous solution, which means it will completely, 100% to the right, give all of its hydrogen ions to the water molecule to form hydronium ions and nitrate ions. Okay? If this starts out 0.02 moles per liter, okay? If it's truly a strong acid, it will completely break up. So 100% of this is gone and gone. The stoichiometry is for every 1 mole of this that donates hydrogen ions, we produce 1 mole of this and 1 mole of this. So if this started out 0.02 moles per liter, I don't change the volume. This concentration is going to be 0.02 moles per liter once that fully breaks up. Therefore, concentration of the hydronium ion in 0.02 molar HNO3 is going to be 0.020 moles per liter. pH function, that's the negative log base 10 of the hydronium ion concentration. So negative log base 10 of 0.02 molar. And simple calculation. Okay. So I get a pH that looks like, I'll put it down here, 1.698 sig figs. Okay. I have two significant figures. You start counting here. That one's significant. That one is. So we have two significant figures, which means I'm going to have two decimal places. So this is the last, that's the second decimal place, last sig fig. So this is going to be 1.70 for my pH. Okay. On the pH scale, 7 is neutral, 1 pretty acidic. Strong acid in aqueous solution makes sense. This is very acidic. Okay, all right, very simple treatment for strong acids. Memorize the 6 strong acids. The problems involving pH calculations, super easy. All right, then we're going to move on to strong bases. Annie's bored, so she kind of wants to play. All right, so now we're interested in how we deal with calculations of aqueous solutions of strong bases. All right. So first thing, we need to recognize a strong base when we say it, okay? So strong bases are your group 1A cations or 2A cations that are hydroxides. Okay, we always have to have some exceptions. The exception is beryllium and magnesium. Those are small divalent cations. They hold on a little too strong to let the hydroxide ion go. So those are going to be weak hydroxides, weak bases. Okay, so who am I talking about? Well, like NaOH, KOH, rubidium, calcium, so on and so forth. So hopefully you can recognize a strong base, group 1 and 2A, hydroxides with the exception of beryllium and magnesium. I'm going to let Annie sit. She's done enough work for now. All right, so let's select one of these and say, okay, what happens if I put a strong base in solution? Okay, calcium hydroxide, okay, is going to be, you put this in water, what's going to happen? Okay, fully dissociates into calcium ions, the cation, and the hydroxide ion. For every one of these that breaks up, okay, calcium, group 2A, charge 2+. Hydroxide, okay, polyatomic ion, charge -1. For every one of these that breaks up, you get 2 of these in solution. Okay, very simply. Now, why is it a strong base? Well, you've produced the hydroxide ion, which is the strong base. Okay, hydroxide ion is going to go next with hydronium ions. It's going to take the hydronium ion and form H2O and H2O. Okay. All right. So technically that's what happens when you put a strong base in solution. For the most part, you don't need to really worry too much about that. The critical thing is when you put a strong base in solution, it's going to fully break up into the hydroxide ion. If we started with a solution that was 0.068 molar in calcium hydroxide, okay, what is the hydroxide ion concentration in the solution? What is the hydronium ion concentration in the solution? And what is the pH? All right, so calcium hydroxide, strong base, 100% in water, breaks up into calcium ions. And for every one of these that breaks up, 2 hydroxide ions. Okay, this starts out 0.068 moles per liter. Okay, 100% of it breaks up into solution. For every one of these that breaks up, we get 2 of these. So the hydroxide ion concentration in the solution is 2 times 0.068 moles per liter. So this is going to be 0.136 molar. All right, so that's how the concentration of the hydroxide ion. All right, so we are in aqueous solution. So I said whenever we're in aqueous solution, we know that the product of the hydronium ion concentration and the hydroxide ion concentration has to be that number at 25 degrees C. Okay? So if I know the hydroxide ion concentration, I can calculate hydronium ion concentration. That's simply going to be Kw over the hydroxide ion concentration. That's 1 times 10 negative 14. And my hydroxide ion concentration, I said, was 0.136 molar. Okay, so that's going to give me okay, 7.353 times 10 to the negative 14. Whenever you're doing these calculations, the units come out molarity. Okay, sig figs. This equilibrium is actually known to many significant figures. I'm limited to these 3, so 1, 2, 3 here. Now, that is your hydronium ion concentration. So let's think common sense. This is a solution of a strong base. Where do I expect the hydronium ion concentration to be relative to neutral water where it's 10 negative 7? Okay? Because there's so many more hydroxide ions than hydronium ions, we would expect a tiny concentration for the hydronium ion, and we have that. And remember, the hydroxide ion concentration was 1.36 times 10 to the negative 1 molar. Right? So on the scale, the pH scale, or the hydronium hydroxide ion concentration scale, this is much bigger than 10 negative 7 neutral. This is much smaller than 10 negative 7 neutral. That's what we would expect, strong base in solution. Okay, final question, what is the pH? I do have a hydronium ion concentration. pH is negative log of the hydronium ion concentration. Negative log 7.353 times 10 negative 14 molar. Last sig fig is here. Okay, and I come up with a value of 13.13. Okay, taking the log, I need to go one more. 13.1335. Okay, I actually had 3 sig figs, therefore I have 3 decimal places. So 1, 2, 3, last sig fig. So 13 point, that's a 3, 1, 3, 3. Okay, once again, does it make sense? I have a strong base in solution, okay? The pH is 13. That makes sense. If pH is 13, pOH plus pH, I always have to add the 14 because of this equilibrium. Okay? Therefore, the pOH of this solution is 14 minus pH, 14 minus 13.133. And that would be 0.866. Okay, so your pOH is relatively small on the pH scale, and your pH is 13. All right, so logic check. Strong base in solution, okay? tiny hydronium ion concentration, big hydroxide ion concentration. Substance fully dissociates. It all hinges on the concentration of the hydroxide ion coming directly from the strong base.